That's perfect. Thank you.
Okay, thanks for the introduction, and I want to say that I'm happy to attend this workshop. I've already learned a lot about dust and the models you have presented. I'm a microbiologist from Aarhus University in Denmark, so I'm trying to follow along, but also think it's important to collaborate across fields, and that is what we have achieved here. So in collaboration with Christian Junker Jørgensen, among others, we have received dust samples from, or dust source samples from across the Arctic, and also some filter samples. And in our research group at Aarhus University, we mainly look at aeromicrobiology and warm temperature ice nucleating particles. And here in these samples here, we found that they are associated with mineral dust across the Arctic in these samples we have analyzed. You probably already know a lot about ice nucleation in the atmosphere, but I will just shortly introduce it here. So the temperature where a droplet freezes in the atmosphere, that depends on several things, right? So if you don't have any ice nucleating particles present, then water droplets are only able to freeze below minus 38 degrees Celsius. And we call this homogeneous freezing. So it spontaneously freezes at this temperature here. But when you have ice nucleating particles present, then they can initiate freezing from minus 38 degrees up until close to 0 degrees Celsius. And they can be IMPs. And here you see an example with an ice crystal, which is the best ice nucleating particles that you have. Or it can also be from an external force, as you can see here, with super cooled water that when you shake it, then it will form ice. Um, so, um, Talking a little bit about ice nucleating particles and clouds. So, ice nucleating particles are part of aerosols, and they can facilitate ice formation in clouds, and this can affect the precipitation, radiative properties, and lifetime of the cloud. So if you have a cloud consisting of only super cooled water droplets, these are usually small droplets that have a high surface area or large surface area, which creates a high albedo. But if you introduce IMPs into this cloud, which is between minus 38 and 0 degrees Celsius, then they can initiate the ice formation. And then the ice crystals can grow at the expense of water due to the lower vapor saturation pressure of ice crystals compared to water. And eventually you will have precipitation. And I want to, yeah, and then the lifetime of the optical density of the cloud is lowered, and more short-wave radiation will hit, for example, the ocean and heat up the ocean, right? And I want to emphasize two things. One, that these mixed phase clouds are especially prevalent in the Arctic. So that's why we are also interested in looking into these high latitudes. And then also that we have some ice nucleating particles called biogenic IMPs, or ice nucleating particles. And these are important at relatively high sub-zero temperatures from about 0 degrees to minus 15 degrees. But what are these biogenic IMPs that I'm talking about? Well, they are a class, or they belong to bioaerosols, which is a class of aerosols, right? And you can define the primary biological aerosols as biological particles suspended in air, and they can include microorganisms and their products, and they encompass all sizes, just as abiotic particles, so from ultrafine up to coarse particles. And it can be protein, viruses, bacteria, fungal spores, or pollen, as you can see here. Then a subset of these bioaerosols can act as IMPs. And in this graph represents the standardized IMP concentration in the atmosphere, where you can see that dust and minerals, they are much more abundant than biogenic IMPs, as you can see here, but they tend to initiate ice formation at a lower temperature compared to biogenic IMPs. And we also observe in clouds that even at these high sub-zero temperatures, we observe a fraction of clouds that are on ice crystals. And this is where mainly the biogenic IMPs are responsible for this formation. We also recognize the secondary ice formation that can happen, but at least we found some concentrations of these biogenic IMPs in the atmosphere that can account for this that we see here. So where are these IMPs coming from? So sources of these atmospheric biogenic IMPs in the Arctic can be from actually every environment that we have, from the Arctic Ocean or from terrestrial runoff, thawing permafrost, and also vegetation, but also riverbeds, glacial sediment, which creates a lot of this dust in these areas here. And they have been linked to yeah, these warm temperature IMPs have been linked to dust events in the Arctic as well. But who are the producers of these biogenic IMPs? So the most well-known producers are bacteria, and we have a handful of members that belong to these genera of bacteria that you see on the left side. And the special thing about these bacteria is that they can produce a ice-nucleating protein, as you can see here in the figure A. And these proteins are bound to the cell membrane, so they are associated with the bacterial cell. And they are long monomers that can assemble into oligomers on the outside of the membrane, and then it elevates its ice nucleation activity. And down here you see a model of the structure of this ice-nucleating protein from one of these genera, Pseudomonas syringae, based on AlphaFold. It's a prediction tool which can predict a protein structure. And you can see it consists of an N-terminal and a C-terminal, and then you have this long repetitive region consisting of 60 repeats of a specific motif. And this can then organize or bind to water and ice, and then it can form this ice grid-like structure of the water molecules and start the ice formation. And these bacteria are known plant pathogens, so they have been associated with agriculture, but are also found in the vegetation in the Arctic. But then other microbial organisms can be algae, and they can also produce these ice-nucleating particles. It's mainly exudates that are not associated with the cell membrane, but these exudates can assemble into larger complexes, and then they get this ice nucleation activity as well. And then maybe a little bit more interesting compared to all the work that you're also doing, then we have the fungi IMPs. And it's fungi that can produce compounds that have ice nucleation activity. And these compounds can bind to minerals or dust particles, soil particles. And we have seen that they have been transported through these riverbeds and terrestrial runoff and into the ocean as well. So they can be transported a long way with the dust. But why do we at all focus on biogenic IMPs when they're so rare, right? So according to the IPCC report, we are not really good in estimating aerosol cloud interactions. And some studies have suggested that bioaerosols drive these large uncertainties in our models because we have limited knowledge on high temperature biogenic IMPs, especially at these high temperatures in the models. So to improve climate models and maybe also get better inputs from the biological side on the models you are working on, we need to better understand these biogenic IMPs, and that can be in regard to their source environments, but also the types of IMPs. Yeah, sorry for this maybe a bit boring slide, but this is the samples that we have analyzed. So we received some source samples from Christian's group, which has been collected mainly in Greenland, as you see here on the left side. And here we have tested the effect on ice nucleation activity if they have been oven dried at 60 degrees or not, because these biogenic IMPs, they are mostly heat sensitive, so they lose their activity if they are exposed to heat because the proteins will denature, right? And then we also received some filter samples that were introduced into this SESAM simulation chamber at the LISA laboratory in France. And here the aim was to mimic saltation and blasting at a flow rate at 30 liters per minute. And then we have analyzed the PM10 aerosol size fraction, which was collected on Teflon filters, for ice nucleation activity. And you can see the samples are both from Canada, Greenland, Svalbard, and Antarctica. But how do we measure this ice nucleation activity in our samples? So in our lab, we have a instrument which we call the micro penguin. And here you can see it. It consists of a cooling base, an infrared camera, and then some water cooling. And the principle here is that we can take our sample, and for example, this dust samples, we mix it with millicube water, and then we can aliquot this millicube water into a PCR well plate into 30 microliter droplets. And then we can submerge it into a gallium bath. That's a metal that melts at 35 degrees Celsius. So you get a really good conductivity between this plastic tray that we have and the cooling elements in our sample or in our instrument. And then when we have when the gallium solidifies again, we can cool it from 0 degrees down to minus 30 degrees Celsius. And then the infrared camera can detect when the water droplets freeze, and it will appear as these white wells here because it emits heat when it freezes, right? And then you can end up with a frozen fraction curve that which I have illustrated here based on this Advent-Dalen sample that we got. And it's a cumulative curve, so the camera detects at what temperature the droplet freezes, and then when all droplets has frozen, then you have a frozen fraction of 1, right? And then if you assume a Poisson distribution of IMPs within these droplets, then we can use this equation from the 70s to calculate a concentration in our sample. And we can estimate it based on this equation here. So if you wanted at, for example, minus 10 degrees Celsius, we can get the concentration per gram of soil material or sediment material in our sample. But if we then take a look at our results, here you can see the results or the ice nucleation concentration. It's IMP per gram of sediment, and here you have the temperature, both from Advent-Dalen and these places in Greenland, Kangerlussuaq and Vestervig. And we do dilution series because if our samples are saturated of an IMP that has activity at a specific temperature, then we don't know if there's one IMP in each well or 100 IMPs active at that temperature. So we dilute it to get a broader temperature interval here so we can estimate our concentration. And in yellow, you see the oven-dried samples, and in blue, you see samples that have been air-dried. And it actually seems like that there's no drop in ice nucleation activity when you oven dry it at 60 degrees Celsius. So it doesn't seem like that it's bacterial IMPs that we have in our samples because they typically reduce the activity or deactivate at around 40 degrees Celsius. But these fungal IMPs, they are more heat resistant and can resist this heat between 60 and maybe up to 90 degrees Celsius, and we need to look further into that to better understand it. And the thing is also that we know that this ice nucleation or biogenic ice nucleation activity is present in many different environments, and sometimes we see this activity in our samples without actually see the responsible compounds or microorganisms that we know for now. So I think there's a opportunity to really discover new particles and also new microbes that can produce these proteins or particles. But we also received these filter samples, which was introduced into this simulation chamber. And they are both from Greenland, as you can see here, Canada and Svalbard and Antarctica. And the main thing from this is that the majority of them, they were able to aerosolize dust particles, which are associated with high temperature ice nucleation activity. And especially this sample from Adventdalen, it's really high in activity. And this value you have here, it's per liter of air, and I want to calculate per gram of material because I think that is more representative for this kind of study, and also to introduce perhaps into models. But here in Antarctica, we don't see that high activity, and that is also what we typically see from samples from Antarctica. It's usually lower in activity. And also, I guess there's fewer areas in Antarctica that are exposed terrestrial surfaces, and the Arctic, no, sorry, the Southern Ocean is not as potent in this activity as in the Arctic Ocean. Then I want to, here at last, just focus on the sample from Vestersvig and Adventdalen, because here we heat treated the samples at 95 degrees for 90 minutes in a water bath to test for heat-sensitive isonucleating particles or proteins. And we see a reduction here, but usually we see a reduction to below minus 10 degrees Celsius. So this discrepancy you see between the two curves, that can be explained by biogenic IMPs, but there might be something else that we don't know yet that has this high isonucleation activity. We know one bacteria that then can produce a molecule that is not a protein. It's a secondary metabolite, so it is more heat resistant, but we don't know that much about it yet. But a future test could be to perform hydrogen peroxide digestion tests so we can further determine the contribution of organic substances to isonucleating activity. And then you probably know more about this than me, but we also have this K-feldspar properties of the dust particles that can be very active isonucleating particles or dust particles. But what we know for now is that the concentrations in the atmosphere cannot account for the concentration of the K-feldspar in the atmosphere cannot account for what we actually observe in our samples. But this hydrogen peroxide test could be a way to test for this K-feldspar. Yeah, and I would be happy if you have any comments on this. Yeah, if you have time for that. So thank you very much for your attention, and be happy to take any questions. I know it's a bit different topic this compared to what you're doing.
Have you got any questions in the room? Oh, yes.
Just a short comment or question. I didn't see that you mentioned also the biogenic marine aerosol. I'm not quite sure how active these particles could be in the northern seas or so, but I know that these particles also are cloud forming, cloud forming.
Yeah, so the marine, like the oceans as a source of biogenic IMPs. Well, I've done some studies in Greenland from Disco Island, mainly focusing on marine IMPs or marine biogenic IMPs. And we see that there is high concentrations and also active IMPs in the coastal areas in the Arctic. And we are trying to figure out if it's microbes in the marine environment that produce these compounds that are isonucleating active, or if it's mainly coming from terrestrial runoff. We see an correlation and also association with terrestrial runoff into the oceans, and they contribute to high inputs of biogenic IMPs. But several studies have also shown that in open ocean areas, the sea spray formation, the sea spray has a lot of organic material, and these algae that I also briefly talked about, they have shown that the exudates from the algae are also carried along with the sea spray.
Okay, thanks.
Okay, thank you. And we've got just one online from Norm.
You say Norm?
Yes.
Oh,
Yeah.
I wonder, I'm really going to ask you a different kind of question, and
Yeah.
that is, have you ever seen MODIS images of Alaska? The dust is coming from Alaska on into the sea. You can see the dust plumes, and then you can swear that at some point they turn into cloud particles. What would be your reaction to that? What would you say about something like that? Is it a kind of a proof of nucleation, or is it too far-fetched to make such a conclusion?
So you're saying that these dust plumes are creating clouds, right? Or cloud seeding
Yeah.
particles. Yeah. I mean, I'm probably not the best to answer that, but of course we know that dust is like the most important one of the most important both ice nucleating particles, and also it can be cloud seeding particles, right? These cloud condensation nuclei. But they are usually not active at these high temperatures. So we mainly focus on temperatures that are higher than minus 12 degrees Celsius, because here it's just a minor fraction of dust particles, or I don't know, with this K feldspar that I also talked about, that can be responsible for ice nucleation at this temperature, unless you have secondary ice formation, see, like fraction, or what do you call it, splintering of ice crystals from higher altitudes, and then it's seeding these low altitude clouds. Yeah. I'm not sure if that was an answer to it, but some thoughts at least.
Well, I needed some kind of reaction. That's a good one.
Yeah, thanks.
And maybe just a quick one from Christian before we move on.
Yeah, well, thanks a lot, Christian, for an excellent presentation. Well, you've been
Thanks.
trying to convey this message to me many times, and I think I finally got it. So, no, jokes aside, it was really good.
Yeah.
One question, though, that we struggle with also in terms of, really trying to quantify real dust in ambient dust. What is your opinion about, based on the preliminary work here now, that sediment samples collected at various locations, stored for various points of in time and under conditions, how useful would they be for further studies for you compared to samples that would be actually collected in the air and then stored with the golden standard?
That's a good question, because I think it's very different from working with just or not just, but with sorry, with inorganic material and then organic material, because when you have biological activity, then you change the composition of both the microbes but also the products of the microbes in the samples if you store them at, let's say, room temperature. So it depends on if you store them frozen or how arid it is, or how dry you store them. Because if you don't have any water activity, then you also have really a low microbiology activity in the samples. So I would say if they've been stored dry, or if you have air dried them and then stored them, then it's still useful. These proteins are quite how do you say, like robust, and it would take some time for them to degrade. But the best would be if they are frozen right after you have sampled after you have collected your sample. Yeah. So it really depends on how you store them, I would say, but it's of interest to us as well, and even though that it has been stored for a long time, I would say.
Thank you.
Thank you very much, Christian. Should I stop the recording and do a new one?
No,
Just keep-
we can have it as a whole section. Thank you.
So the next talk is by Philippe Gavin-Bourdon. You're there online, and the title is On the Importance of Episodic Coarse Aerosol Emissions, Long-Term Observations of Aerosol Mass Concentrations at Eureka in Canada. So if you're online, you can present. Let's see.
In the contract, there he is. Yeah.
Perfect.
Do you hear me?
Yes, perfect.
Okay, perfect. And I'll share my screen.
Yes, great.
Perfect. Yeah, are you seeing the
Yes, that's
Yeah.
great. Thank you.
right
No,
slide? Okay, perfect. All right, so hi everyone. I think I'm really kind of glad to be presenting today, and I think my presentation will fit nicely with the previous one, which basically introduced a bit kind of my subject and in a sense the motivation perfectly. So just in terms of like generic motivation, why we are basically concerned about aerosol concentration is exactly as the previous speaker said, in terms of radiative forcing and kind of the interaction with cloud. The particle will have either a direct or indirect effect and change really kind of our radiative balance, but also mainly when and so kind of, I should say, the station when kind of where we're working on in the Arctic has been collecting particle and kind of measuring particle concentration for a long time, but the focus in past studies have been a lot on kind of smaller particle and some micron particle, and with the current project, our kind of goal was to expand basically this observation and kind of report more on kind of the coarse mode. And so larger particle that had more mass and were potentially kind of better contributor to fertilization of the ocean, bringing nutrient that possibly essentially could also change just the balance of emission in the region in terms of the biogenic emission by the ocean there. And so presenting here just in general, like I said, the main research goal was to monitor and characterize the particle size distribution and the temporal variation over time, which basically I talked a bit more about the general trend and kind of the general temporal variation in a past presentation 2 years ago, but we basically now kind of expanded into trying to also kind of identify more interesting event of coarse mode emission and to provide possibly a way with kind of our data set to help in remote sensing or model validation and kind of to highlight how the really kind of extreme episodic events were important and kind of basically provide kind of a in situ proof and in situ case for really kind of the importance of looking at high resolution and not just overall kind of background or constant concentration or kind of average. And so for context, when we're talking about Pearl or Eureka, it is shown on the map right here. So it is located on Ellesmere Island in the Canadian Arctic archipelago. And there is technically two sites, one being Pearl or the Ridge Lab that is at 615 meter in altitude, and the Opal or the zero altitude lab that is essentially at sea surface. And for kind of our study or kind of for the data set that I will be presenting now or presenting today, all the data was collected at Pearl, so higher up in altitude, but just so you know, currently the instrument have been moved to Opal, closer to the physical meteorological station for kind of ease of maintenance as of 2024. So we're hoping to be able to have a certain kind of comparison also in the future between the different kind of location and basically the different years, see if the altitude change the concentration observed. But in terms of instrumentation, so what we're working with, you have kind of just a general view of our collection site. So we have an inlet on the roof of right here, on the roof of the lab here, pulling here inside, and with an SMPS and an OPC, we're measuring particle ranging from 10 nanometers to 10 micron at approximately a 3-minute resolution. And the site, the instrument have been running more or less nonstop, minus some maintenance period since 2000, end of 2015. So for kind of, we have basically 10-year data set now of particle size, distribution, and some kind of particle concentration, which, I mean, like Aldona alluded to, is really rare in the Arctic and really valuable. So from those 10-year, we looked at the seasonal variability of the particle mass concentration over those 10 years on average. And so you have a representation here showing really from our data set, we're seeing overall higher concentration, we're kind of build up really of the concentration from December, leading to approximately a peak in April, where the median concentration is really the highest, and really small mass concentration in the summer to be expected, with just in general smaller particle being present in the Arctic. But one thing that kind of we were interested in and kind of surprised about is when looking at the 90th and 95th percentile, it's kind of really these peak and the increase in the spring and the fall of shoulder season being subject to an increase in the the supermicron particle concentration, and an increase in basically extreme event, or kind of the 10% larger event. And so to kind of try and see if we were able to identify or isolate those event and see if there was kind of any underlying composition of particle that we were able to kind of observe. We ran the 9 years, the first 9 years of data we collected in terms of particle size distribution, and ran it through k-mean algorithm to identify kind of underlying or defining modes and defining shape of particle size distribution observed. And so here on this slide, this is basically a representation of the average particle size distribution, and with the shading representing one standard deviation interval around that mean of the average particle size distribution represented by each of the cluster reported by our algorithm. We had, and we looked at when we were specifically observing those clusters, mainly being interested in seeing when are we observing, kind of how many times are we observing these really high concentration of 5 micron and 2 micron distribution. And so here we have a representation of the number of days when each of the cluster labeled H5 to LS. So the H and I should say, yeah, L and H just being a representation of the relative intensity in concentration, and the second S2 or 5 being the modal diameter. And when looking at here the frequency, we see that we have kind of two different kind of bit regime, where some three of our cluster L colored in red, L5, H2, and H5. So mainly the higher mode and kind of high concentration cluster were observed overall less than 10 days per month at essentially any given point in our data set. And so wanted to kind of dig a bit deeper and kind of seeing, okay, what is happening on days when we're observing those clusters compared to kind of the more background that were really observed ubiquitously over the 9 years. And looking at what was the course mode fraction and the the course mode fraction and kind of the regime during those days. So I'm here for the whole time series in terms of the average total mass concentration colored in the contribution of the submicron modes versus the course mode mass in blue and red respectively, with the purple star representing the months when we observed those episodic cluster only. So overall, a bit as expected, the course mode is dominating the mass concentration, but we can see that not every year first is observing the episodic cluster in kind of all the given months, but there's also seem to be kind of an acceleration of the number of time that we're observing those episodic clusters since 2019 approximately. And looking, I'll just kind of show kind of maybe a case study, but looking at when we were observing those cluster, we looked at what was the meteorology, trying to differentiate whether it was more kind of an influence of local versus long-range transport from just generic modeling. I'm representing here, for example, in kind of April, vertical distribution of total mass concentration reported by simulation done in the global JustChem model with the contribution of each particle type that the model is considering, and in general, kind of according, or basically in accordance to the known literature, we have contribution of really a bit higher up aloft transport of dust that is generally associated with Asian dust. But when looking at the methodology of the clusters that were kind of episodic at our site, you have here on the top right a wind rose representing so the distribution and the wind speed observed when cluster L5 was observed. That is one of our episodic cluster, and we had in general high wind speed contribution and kind of high contribution of high wind speed from the southeastern location that correspond to the general location of dust source that were identified here on kind of the southeastern bank of the fjord where Pearl is located by group like Normal group with and Aldona's group also with basically kind of the presentation we just had, and Ali Said also presented last year in his work on identification of dust source in the region, with kind of the paper coming on. And we also kind of just have an example with a photo here at the bottom of kind of possible haziness and kind of the from Pearl and from Eureka, what basically the region looked like. But to kind of confirm that, because that was just kind of in situ, we weren't able necessarily to link directly the dust or necessarily define kind of dust. Just to make sure, we also ran backward trajectory using iSplit on days when we were observing those clusters. And so here we have a case for more month of October, where in general we have trajectories coming from over Greenland, and especially along the coast of Greenland, where we know that there are also these type of glacial valleys that are producing dust without necessarily being able to simply isolate or single out these clusters as being only dust being presented. This is, for example, only one case study or one event or one example, but in general, kind of the cluster themselves represent more a mix of sea salt and dust, but definitely we have kind of events that are more likely to be kind of purely dust from these two examples here. But we still have essentially cluster that were representing really extreme event of large concentration emission. And so we wanted to kind of see how much were those cluster contributing to the average mass concentration. And that bring me basically to this kind of last figure here, where you have the daily average mass concentration for each month observed at the station, represented here, with the what we call basically regular or kind of more background concentration, with what is the mass contribution of the submicron mode in blue and coarse mode in red, with the lighter color being only the months where no episodic event at all was measured. The more saturated or kind of the brightest color being the month where episodic event were represented, with the bar being the error bar and the standard error associated with these average. And we have basically approximately a doubling of the mass concentration in months when we have episodic event. Just to make sure, we'd also kind of looked at what was just the background. So what was the average mass concentration on months where episodic event were considered, but without the without the days where the episodic cluster were observed, to just basically make sure that it wasn't only an overall increase in mass concentration creating the observation of those cluster, but that it was really kind of a different regime and different particle that we were observing. And you can see with kind of the middle bar here on months where there were episodic cluster, that without really the days where the episodic cluster, so H2, L5, and H5 being observed, there seems to be a overall increase for most of the months except November in the overall particle mass concentration, but nowhere near essentially the level, and kind of not as significant as when we're observing really the episodic clusters themselves. And so really that bring us essentially to kind of our conclusion that, and kind of we hope that kind of that bring us basically to our kind of conclusion that being able to really look at long-term data set and having in situ measurement that are kind of long-term in the Arctic is particularly important, because if we're just basing our assumption and modeling or retrieval on really short-term and, for example, only kind of month-long, or even most realistically, most of the time you're kind of maybe a couple of weeks at a time in the Arctic, and not necessarily every year, you can essentially come and miss those really extreme episodic transport that majorly change the overall yearly and kind of annual kind of regime, or that will majorly impact basically the environment on a given year, and where if we want to have a better representation really of the yearly variation in the future based on kind of our modeling, consideration of really those extreme transport event is important. So we'll welcome any question if there are some, and if we have time.
Thank you very much. Any questions in the room? Maybe some, yeah.
I think online, yeah, Said has a question.
Go for it.
Can I go ahead?
Yes.
Okay, thank you so much, Philippe, for your excellent presentation. I just had a comment, not a question. I think the dust source that you showed on one of your slides close to Opal, that could be a dust source, but I can say there are like maybe other sources closer to Opal or Pearl station, because that dust source that you showed is like approximately 20 kilometer away from Pearl and Opal station. But I think there is one more dust sources closer to Opal, like 1-2 kilometers away from Opal, that as you are measuring the size distributions using the ground-based measurements. So this is, I think, maybe more reasonable to have dust sources closer to your instrument, because for 20 kilometer away, maybe the coarse mode particles are not that much reaching the opal station. Maybe I'm not sure, but I'm just suggesting things. But I thinking there is another source closer to opal station. Yeah, that's it. That was just a comment. Thank you for your nice presentation and results.
Thanks. No, I think you're absolutely right. It's definitely not I think the point I showed is definitely not the only dust source, basically, around. If we're looking at more kind of global back trajectories, anyway, it is possible that the emission or what we're observing is not necessarily coming from like only basically the fjord around Opal and Pearl. So yeah, it's not possible to kind of attribute the emission from a single source.
Good.
Thank you very much, both of you. And so we'll move on to the next talk now, if no one else has any other questions. Okay, well, thank you very much, Rudy. Thank you.
Pleasure.
Okay, and so the next talk is by Catherine Moore, and the title is Improvised Representation of High Latitude Mineral Dust Sources in the NASA GEOS Model. So I think we're ready to find out. If you want to maybe just flip the view.
Yeah, I was going to just ask which one it was showing. One second. Is that better?
Yeah, that looks good. Great. Whenever you're ready, thank you.
Okay. Thanks for having me. So I'm a postdoc at the University of Maryland and also NASA Goddard. So hi, Santiago. Nice to see you this morning. So I'm going to be talking today about what we're working on to actually add high latitude mineral dust sources to the NASA GEOS model. And I just wanted to sort of highlight this image that I pulled, which relates to what Santiago was talking about earlier. So this is showing the Copper River Delta for those that aren't familiar, and it has frequent large dust emission events that you can see quite easily from satellites. So one of the main driving factors for this research in particular was that global models often don't have high latitude dust sources, but they can be regionally important. So on the left, I'm just showing what sort of the standard topographic emission function that's used in GEOS and a lot of other global models is. And then on the right, I'm showing some of Christine Groot-Swaftink's work from a few years ago now, but it's showing the surface concentration of dust, and the blue is representing local high latitude sources, greater than 60 north on the left and greater than 80 north on the right. And then the sort of light red and orange colors are showing remote sources. And so if you're concerned with things that are happening close to the surface, the local sources are actually more important than the remote sources at all times of the year. And the reason that I care about this is sort of going back to what Christian was talking about a few talks ago, is because these high latitude dust particles can be really important in both the Arctic and the Antarctic for ice nucleating particles and cloud glaciation. So I wanted to show an example from sort of both poles. So on the left is the a co-location of a dust plume, which you can see in the left figure from the DREAM model. And then on the right, the sort of blue colors are showing ice in clouds in this region. So there's a pretty good correspondence between where we have this dust plume and where we have ice in the clouds. And this can be seen in other areas as well. And then on the right, this is a modeling study that came out a couple of years ago from a group in Japan. And they simulated local dust IMPs to be over 60% and up to 100% of the total in the boundary layer. So you can see, depending on whether you give them a low or a high IMP activity, you get a different answer. But either way, they're still the vast majority of the total. And so they can be really important for the low mixed phase clouds that Christian mentioned as well, which are very common at both poles. So to start with, we wanted to use Christine's map that she developed a few years ago. So this is just showing what her flex dust emission map looks like over the Arctic. And then in the dots, I'm showing a couple ground sites that I'll talk about a little bit more later. So some of the sources in this map include the Canadian Arctic Archipelago, which Philippe just showed, Greenland, Iceland, Svalbard, and there's some other regions as well. The high latitude emissions are generally smaller and more seasonal than the low latitude sources, so it's not very interesting when you plot it on a global map. And then one of the things that we specifically wanted to look at is the seasonality in the snow and ice cover, vegetation cover, and the soil temperature, because these don't occur as much in the large low and mid latitude dust regions, and so they're often not actually accounted for in the model. So I'm going to skip through this a little bit quickly, but if anyone has questions, I can go back to it later. So I'm running GEOS at a fairly high resolution for a global model, but not high for a regional model. So it's 1/2 degree resolution. We're hoping to go down to 1/4 degree resolution soon. I'm running the GoCart 2G aerosol, which is similar to what would be in GEOS Chem, if anyone is familiar. And then I'm running both the Jeannot dust emission scheme, the Flex Dust dust emission map, and then I'm using essentially nudged simulations to constrain the meteorology, but not the aerosol, so that I can compare all the simulations on a temporal basis. So I'll start with sort of a general overview of what we found. The top panel here, or the top row here, is the sort of baseline case where we have an emission map that only has mid and low and mid latitude dust sources. The middle row is the flex dust map that has sources all the way out to the poles. And then the bottom panel here is the flex dust map where we account for things like the seasonality in snow cover and vegetation. So just to compare the sort of top two rows across a couple of different months, they look pretty similar, and we're getting basically similar transport from the mid-latitudes in both of these cases. However, once we account for the reduced emissions in the high latitude region due to snow cover, soil temperature, and vegetation cover, we reduce the AOD across all these seasons. And so that's showing that the high latitude sources were quite important, and the mid latitude sources may also be affected by some of these changes to vegetation, for example. I wanted to show here some of where we're getting sources from and how that changes seasonally. So the top panel here now has the flex dust map, but it is being filtered for the vegetation and the snow. The bottom one here does not have those. So if it was a source at any time in the year, it'll appear throughout the year. So we see sources where we expect them to see: Greenland, the Canadian Arctic Archipelago, things like that. But you do see a change in the seasonality when you account for differences in the vegetation fraction, for example. So we see more emissions in April when we don't account for vegetation, and you reduce all the emissions in the winter on the very left in January when you account for the snow cover. And so those are physical and what we would expect, but it's important to know that some of the global models don't have these parameters in them because they're not important for the main dust emitting regions at the low latitudes. And then I wanted to show the same figure as before, but now we're plotting the fraction of the high latitude dust mass at the surface to the total. So the pink colors are showing that the high latitude dust mass is the largest fraction of the total dust. And then the sort of blue colors are showing that long range transport is more important. And this varies seasonally, as you can see, but especially in the summer and in certain regions, we can get 80 to 100% of the low level dust concentration is coming from sources above 60 north. And that's in agreement with what Christine has shown and other groups have shown, but it was a good check that the GEOS model could also represent these sources. And then this is sort of a time series view of that same parameter that I just showed you on the top. So these simulations I ran for about 2 years from 2019 to the beginning of 2021. And in the top, we're showing the surface mass fraction over those 2 years on a monthly average over the whole Arctic. So you can see that the contribution of local dust peaks in sort of late summer, early fall, which is what you would expect for the high latitude emission season. But there is a non-zero contribution at all times of year, depending on which simulation you look at. And then you see an increased influence from long range transport in the winter, which is, again, what we would expect. And then on the bottom, I wanted to highlight the dust emission fraction coming from the high latitude regions versus the rest of the globe. So these estimates are, there's not very many of them, but they generally are in the range of 2 to 5%. And in my simulations, we're getting less than a 1% contribution of the high latitude sources to the total emissions. So we're looking into this. We're not sure exactly what's going on, but because there aren't very many estimates, this could be also a reasonable estimate in the range of uncertainty. One thing that I'm hoping that I can get some feedback at the end is I'm working on creating a ground site data set of dust concentration in the Arctic and the Antarctic. So I'm using an improved type method to calculate dust mass from aerosol elemental measurements. And some of the sites that I'm using are shown in the map on the top right. So Willem, Zeppelin, sites in Iceland, a few in Norway, and I've also got two improved sites in Alaska that I don't have on this map. And this is an update to the improved method where it uses regional values to get a better estimate of the dust mass for different regions. But unfortunately, high latitude was not included in the regions that they had. So I've been compiling also some high latitude sediment and geochemical data to estimate some of the values that I need that are in that equation on the top for the Arctic specifically. So if anyone knows of any more geochemical data from dust source regions or more aerosol measurements of chemical composition, I'd be really interested to talk to you. And then the last thing that I wanted to, or one of the last things I wanted to briefly show is another way that we're sort of approaching evaluating this simulation data is with a product from the Calypso satellite. So there's a couple of groups that have been trying to infer dust AOD from LiDAR data. So from Calypso, now from EarthCare, from Aeolus, similar types of instruments. And so we're working with Vasilis Emeritus's group at the National Observatory of Athens, and these figures were made by one of his postdocs, Manolis. So this is just a case study to test whether their method would work at the high latitudes because they hadn't used it outside of the Dust Belt region before. So here's a case from Iceland in June of 2019. On the top right is the Calypso aerosol type that comes from their standard algorithm. And we are interested in the sort of yellow colors and the brownish colors, which are dust. And then on the bottom is an example of what their retrieval can return. So in addition to the mass concentration I'm showing here, which is a very derived product, they also have dust extinction, which is a more direct estimate coming from the satellite data. These are all based on depolarization to pull the dust component out of the total signal. And I just received a gridded data set from him that we're going to try to use to do some model validation. So hopefully that will provide some interesting results, but it may be useful for other groups as well. And then the last thing that I wanted to talk about that we're working on right now is to see whether we can improve our estimates of dust emissions by using a more detailed source map. So the two that I've shown so far were erodibility-based topographic dust emission maps, Paul Jeannot's from 2001 and Christine's from 2016. And they may not capture the small scale of high latitude dust emissions well, at least in a coarser resolution global model. So we wanted to try using a geomorphology-based map, which have been derived more recently, and they account for the sediment supply and preferential dust emission locations at a very high resolution. So the map that I'm plotting here on the right is at 3 kilometers. The native resolution is about 50 meters. And so this particular map, which is from Perjuli and Zender, has been added to GEOS, and I've been starting to run some simulations with it as well. It looks right now from our preliminary testing that it's overestimating dust sources in the Sahara in particular, and so we're looking into that, but I'll be really interested to see what it does at the high latitudes in particular. So I'll just quickly summarize what I showed today. Many global models have poor or no representation of high latitude dust, and that impacts their ability to reproduce both direct and indirect radiative forcing effects, such as from clouds in the Arctic and the Antarctic. When we add high latitude sources to the GEOS model, we get similar results to other studies, which suggest that local sources dominate the low altitude dust budget in the Arctic in particular, and especially in the summer. And when you add seasonally varying dust emissions, which are modified by vegetation, snow cover, and soil temperature, you change where and when the high latitude dust is emitted, which makes it a little bit more physical. And then we are currently working on improvements to the source map, which I just showed you, updates to the emission scheme, and then some of these data sets to validate our model. So I'll stop there, I think. Thank my funders, and I'll take any questions if there's time.
Thank you very much, Catherine. Is there any questions in the room? Anyone online, maybe? Yes, Brian?
Yes, thanks. Great talk, Catherine. I just had a quick question about your remark about the source function. Did you compute that at the resolution that your model's running at? So using sort of the Janot formulation?
The one that I showed at the end?
That's the geomorphology. So or the topographic source function used in
the Janot topographic function and the flex dust one. No, they're both at a higher resolution than the model is running. I would have to double check, but I think about 10 kilometers.
Okay.
But they're not as high resolution as this one, which we're going to try next. And the other advantage is that the topographic functions have a smoothing applied to them to deal with the topography, essentially. And so we're wondering if having closer to point sources in a map like this based on sediment supply will help us, but we're not sure yet.
Okay, so if I remember correctly, you ran the model at half of the grid resolution?
Mhm.
And so you had a topographic source function that was computed at much higher, and then did you interpolate and then
Yes.
feed that? Okay.
Yeah,
And
the model does that internally, so you can feed it a source function at a higher resolution, and the emissions can take place at that, and then it will be interpolated and combined when it goes into the atmosphere.
okay. Okay, thank you.
Thank you very much. I think we'll move on and try and keep some of the time. So thank you very much. Okay, so the next talk's by Pavla, and she'll summarize high latitude dust projects and networks in 2025.
Thank you. We have voted and try to make it very fast. Yeah, so I believe it's quite late, so many of us are already probably tired, so I will try to just really summarize it quickly. Although I have one introductory slide, which is basically, I use it very often if I don't have much time just to summarize the key facts about the high latitude dust. So I thought I could actually also start with this slide here. So the key facts are why actually is so important is that it contributes to the Arctic amplification, mainly through the dust albedo feedback, and that has been summarized in many papers. Then high latitude dust was recognized as an important climate driver in polar regions and in the IPCC report in 2019, but then later on also in the AMAP report in 2021. The most active dust hotspots in the Arctic are often located to ice proximal areas with frequent floods bringing the fine sediments from beneath the glaciers. I'm always emphasizing this for Iceland because people are mistaken that these are the kind of deposited volcanic ashes, which is not true. That's being usually removed within a few months after the eruption. High latitude dust storms cause severe air pollution. Very often, also concentrations are 1,000 times higher than recommended. Well, not very often, but there are some cases when it's even 1,000 times higher than recommended health limits. For example, in Iceland, based on 63 years analysis of the synoptic codes, there are on average 135 dust days reported annually. And we know that the dust can travel thousands of kilometers, both inside the Arctic and also towards Europe. And then the two important points are that high latitude dust has impacts on atmosphere, cryosphere, marine and terrestrial environments. It causes severe erosion and land degradation, as we learn here in Iceland. And it also has impacts on socio-economic sectors, so health, road safety, energy production, aviation, again, the land degradation. And as the examples, you can see the images below, for example, full swimming pools after dust storms in Iceland, or cars damaged with broken windows just within one single event. And these snow dust storms, so you can see the dune. It looks like a dune, but it's basically snow with the dirt on it. And the networks, I will proceed to that. So you hopefully already all know that we have this Ice Dust Association, which is the organizer of these workshops. But to emphasize the kind of global network on dust generally, so important is the activity of the World Meteorological Organization, sent an dust storm warning advisory and assessment system. So this is one of the 19 members of the United Nations Coalition Combat Sand and Dust Storms. It's called UNSDS Coalition. And proudly, Iceland is part of this, one of these three nodes of this WMSDS WASP. And that's the Northern Africa, Middle East, and Europe node. At the moment, of course, during the meetings of the boards, we are sometimes discussing the high latitudes might maybe one day be a separated node, but at the moment it's how is it? And just to emphasize that Iceland is technically, with the eroded areas of 44,000 square kilometers, the largest desert in Europe outside the geographically European Caspian area. And continuing, don't worry. So the high latitude dust active networks as for today is to our knowledge, is the Ice Dust Association, Icelandic Aerosol and Dust Association. Then there is a UArctic thematic network on high latitude dust. Then also the Castenschiold collaboration program. Iceland is, at least in the phase 1, was mainly focused on the dust. And then there were also smaller projects of our knowledge, for example, like Nordast, which was funded by the Nordic Council of Ministers, but that's already over, sorry, it's still in the active part. And so it would be also nice from you if there are other existing networks on the high latitude to add it to this list. And as for the Ice Dust Association, at the moment there are 57 research institutions from 22 countries, over 110 members, and over 60 papers published, which is annually increasing. And also it's an active member of the European Aerosol Assembly since 2022. And based on that, also with cooperation with Nordic Society for Aerosol Research, the 11th High Latitude Dust Workshop will be together with them here in Reykjavik on 9 to 12 February. So you can remember this date. So it will be a rather larger event. So here is the location of the Icelandic Aerosol Association between the European Aerosol Associations. Very happy for that. If you need more info on the Ice Dust activities, please visit our website, which is basically icedust.com. There's also tab on publication. On this website, it's in Zotero style, but if you visit the old website, there it's written basically as a list of references. And not only that, we organize this high latitude dust workshop, but there is also active Facebook website, Dust Terms in Iceland. We shall maybe rename it on air quality in Iceland, or just increase it for the whole Arctic or also Antarctic region if people want to post. And also, since 2017, we have maintained a session at the EGU, which is on atmosphere-cryosphere interaction. So happy to have you contributing there. So this is the link to the UArctic thematic network on high latitude dust. I don't have the list of the partners here, but it's a strong participation also from Canada and the Nordic countries. And basically, it has to be the members of the Arctic Council, but also other non-member countries and their associations, which are non-member in UArctic, can take part. And please just let me know if you want to be added and you want to kind of contribute, because this is actually a really great tool for dissemination and outreach through their news. And then the United Nations Convention to Combat Desertification has introduced Sand and Dust Storm Toolbox, which has been existing already for several years now. But this is a really place to go if you want to find information generally on sand and dust storms, and from their mapping, observation, also source control and management, impact mitigation, risk maps, and so on. And I'm very happy that Iceland has been added, or the activities of the ice dust has been added to this network. And I think it's a brilliant first step. Also, the operational forecast for Icelandic dust is mentioned there. And this is also generally, I think it should be said in this talk, because where it belongs the most, that there is about 3.8 billion people that are really affected by sand and dust storms around the world. And that's why the United Nations climate change is focusing and on this really important and bothering issue, so that the decade of 2025 to 2034 has been declared as a decade on combating sand and dust storms, and that indeed includes also high latitude. So these are the facts, and now I'm just having a few slides to connect to the day before, because this is the link to the sand and dust storm source base map, and it works. So you can find the information, and you can focus on your region, and you can also look at it in temporal scale. That's going to be the next slide, but just to show here, by adding the high latitude sources also into the source base map, you immediately see this northern dust belt. And it was very nice to see in talk, I think from Aldona, that you actually classify the Canadian dust belt, which is slightly located lower than the Siberian, but it still can be merged and called like northern dust belt. It was quite difficult, but it has been defined in the paper of O.T. Meinander. And this is, for example, if you have interest in Svalbard, so here is the sand and dust storm index for different seasons, and you can see the activity in the colors. And yes, I just have to emphasize again, where is the dust coming from, at least here in Iceland, is the glacial activity. These are the dust hotspots. They don't have to be big in size. They can be in terms of maybe even less than 10 square kilometers and smaller, and they produce tons and tons of dust, because as we experienced during the field campaigns in 2021, one flood in the afternoon can bring you up to 28 centimeters of a new material, because the lighter layer means the finer particles are sedimenting at the end. And that's what happened to us. It actually really flooded our equipment. And second important fact is, as you can see on this picture, the flood doesn't prevent the dust from suspension. You have flood, but it's still blowing the dust on the places which are not affected. So at least for the origin, for the volcanic dust, which is high in a volcanic glass. And these are not only sources in Iceland, it's same for Antarctica, the James Ross Island, it's same for Alaskan sources. So we are not the only one. So it is the glacial activity which turns the maximum emission. And then also, when Nichko had a talk about the dark model, so there is this paper where they compare the size of the particle with the color changes and also albedo of the particle itself. So the smaller the particle is, it's in this graph, the albedo, and also a different angle, because the spectrometer was on a movable hand. So from different, like the sun is traveling on the sky. So for the sizes achieved by the smallest size was maybe 125 micrometers. So the smaller the size is, the higher the albedo is of the particle. And it all changes when the particles are wet. So the wet makes it even darker. Then we go almost to the black body of 0.01 reflection or albedo. And that's the case when you have deposition on the glaciers. Of course, they are wet. So the albedo is even lower. So I believe that this paper might help also with these estimates of darkening. And you can see that these samples are basically laying on a black paper, and sometimes you don't even see it, but the size make it brighter. And another network we actually joined since many years, but it has now increased up to 100 glaciers monitoring. So it's called Planet Watch by NLabs. It was agreed first time at the COP meeting in Glasgow in 21, and now just from monitoring of 10 glaciers around the world, now we have 100. And if you are interested in, so our glacier is really dirty. What we are actually looking at here, it's a glacier, the dirty thing in the middle. So if you are interested in the time lapses, you can just go to my Tiki and search for the open projects. Just put Iceland or Katla Glacier, and you can see backwards the quick kind of changes of the time lapses. Not only how the colors change of the glacier, but how quickly it melts. And this is example because it's also very popular for tourists. So we documented the collapse of the very popular Kötülökút ice cave. In the camera, you focus there, and this part in the center, it actually doesn't exist anymore. So that's when it started in 2022. The yellow part is not there; it's gone. There used to be the tunnel. And the last announcement is, and it's exactly now 1 hour ago, they are handing the grants of the Icelandic National and Research Funding Agency. And after 5 years almost of trying, our project has been funded. It's called Dust Hela, Dust Changing the High Latitude. So also from point of Iceland, we can finally focus more on these changes, not only in atmosphere, but also impacts on other parts. And I believe that will allow us also to place some instruments in Greenland and Svalbard. In Antarctica, we are continuously monitoring, of course, in Iceland, because the network here is really sparse. And based on these in situ measurements, we hope that it will help to bring another circumpolar dust forecast model. So thanks, National Agency. So this is the final slide, and yeah, just to again announce the next year of 11th High Latitude Dust Workshop will be a quite big event, and it will be actually also focusing a lot the students' participation, because NOSA, the Nordic Society on Aerosol Research, is very keen on that. So I hope to see many of you here again. Thank you. So are there any questions? In here, so I believe that allows us to move.
Thanks very much, Hannah. That's great.
Thank you. Please don't download the bread. Yeah, they were having that at two, but I couldn't go.
Hey, Paula, this is Santiago.
Hi.
A quick question. You in this last presentation, you shared a lot of resources like websites and new cameras and places to check. Do you have that? I mean, because it was all in a screen, I could not check the links. So can you send out an email or put all those URLs in the chat, because I'd be interested to check them out.
I guess the best would be to put it on the ICEDAS website and then send email that it's there, because also the recordings will be there.
Okay. Yeah. Please send out that email. Yes, thanks.
Okay, good.
Yeah,
I don't think he's there. Let me check. He's not there. So, oh yes, in this time it's actually.
Yeah, maybe we'll just. Right, so the final talk for today is by Sophia, and the title was Analyzing Black Carbon in Urban Belgrade with an Etherlometer Measurements. Hopefully I said that okay.
Yes. No.
We can just close the. Everyone will see that okay? Yeah.
I have to start recording.
It's already.
Hi everyone, I'm Sophia, and today I will be talking about analyzing BC or black carbon in urban Belgrade, and I will be following up the presentation that Dragana did yesterday, and a little bit more focused on the correlations and the stuff I did for my master thesis, and yeah. So So I would talk a little bit more about the instrument we use. It is the atolometer model that that can measure mass concentration of black carbon, and also as well it can measure the percentage of biomass burning. So the black carbon is an aerosol that can absorb light, and it can be one ratio of it can be biomass burning, and the other one can be fossil fuel burning or liquid fossil. And so, how is it working? So we have like this paper or filter that is inside of the atolometer, and for one spot of it there is no airflow, and we can measure the intensity of the light that it goes through it. And on the other spot, we have controlled airflow through the spot, and by using those two intensity of the lights, we can calculate the attenuation, and then with time the attenuation, we can measure the coefficient of the absorption, and with that we can gather, or we can get the concentration of black carbon that we use. And also the part of this instrument that is very nice is that it can eliminate the loading effect that happens on this filter sample. So with time, the filter that is not decomposing, that is deploying, or that is gathering, accumulating on the filter sample, it can get saturated, and it can create these values. So with the compensation parameters, we can get just the compensated black carbon that is it's not that is not obstructed by the paper sample. And so this atolometer can also measure the intensity of the light for these 7 different wavelengths. And what we did, we just used the coefficient of absorption for the wavelength of 880 nanometers. And that is because in this work by Muller, we can see that that wavelength is the maximum light absorption by the BC. So when we have BC, so like aerosol that is absorption, we can also create, there is also a source of brown carbon that is created when we have slow fires. And with those slow fires, brown carbon is a different structure than the BC. And with this diagram, with absorption coefficient independence of the wavelength, with Rayleigh's scattering theory, we know that it will be a straight line for this function. And the thick solid line depicts the hypothetical absorption of both BC and brown carbon. And so at the wavelengths of, so it doesn't show it on the screen, but at the wavelength of around 880 nanometers, we can conclude that mostly the absorption of the light at that wavelength, it's just black carbon. So we took advantage of that. And also besides that, mineral dust can also absorb the light, but for my master thesis, I also calculated the angstrom coefficient for both quenched and annealed, and I used 2 pairs of absorption coefficient for the wavelengths, so for the corresponding wavelengths, and for all the measurements we have for from this atolometer, I only had values that were above 1 until maybe 2.2, and we just for the mineral dust, we said that it wasn't present at this urban part of Belgrade measurement. So the measurement from atmometer lasted approximately 7 months, and as well as that, we had meteorological station measurements that measured these 11 parameters. 8 of them were the pollutants, and the last 3 were just physical parameters like pressure, temperature, and relative humidity. And so what I did was, for my master thesis, this is one of the correlations I did for Spearman between black carbon concentrations and the pollutants. And what I did, I put a frequency of the correlations I had for those 2 parameters. So yes, the title is in Serbian, but if you just look the last two parameters, you can see BC and the pollutant that was measured on the meteorological station. And what we concluded is that if the correlation is around 0, you can see on ozone the correlation does not exist, which is the good comparison. And if the value of the correlation is above 0.5 to 1, then it's a strong bond between those 2 parameters. And for BC concentration of the pollutants, we saw that the nitrogen oxide and the carbon monoxide had the strongest correlations, and the strongest anti-correlations was for the ozone. And the physical parameters that have values around 0, which is no correlations, were, I guess, temperature would be the perfect example because its peak is around 0, which is not a little bit more negative and a little bit more positive frequencies of the correlations. So because I have the ratio of biomass burning in the total concentration of BC, I could also calculate the concentration of BC, and I also did the correlations for them and this type of distributions. And the correlations I had before were now no longer the same. So the nitrogen oxide, it's not correlated. It's actually anti-correlated to the BP, which is expected because nitrogen oxide is usually, it comes from a source that is usually fossil fuel burning in the urban area. And the ozone is, again, very anti-correlated, which is the graph that is in the right corner. And again, the physical parameters are very, very not correlated. Again, the temperature is straight to 0 to the BB concentration. What I also did was the scattering plots, which, again, ozone is, I couldn't even have a linear fit for it because there's no correlation between those parameters. And you can see also the nitrogen oxide is strongly correlated. So this is the scattering plot for all the measurements I had. The next thing I did for my master thesis, I chose the weeks in which I would get the scattering plot for BC independence of nitrogen NO2 and for CO, which were the parameters that had strong correlations. And then what I saw when the season changes, when from the week that is in summer until the week that is in winter, the goodness of the graph, or I guess R squared, that is like goodness fit or like regression fit, it slowly decreased, and for CO it stayed above 0. I think I didn't put it in the presentation, but it was between 0.6 and 0.8. Yeah, something like that. For the seasons as they change, it was the same week that I chose. And the last graph I did was also the correlation, but now as the season changed, I chose 2 weeks instead of 1. And I was looking at the dependence of the correlation coefficient with the hour of the day. So what I did, I made an average of 2 weeks and the hours I had the correlation for and put it as the hour of the day. And again, I watched how the seasons changed. And what I saw again is that the correlations of NO2 and BC slowly decreased with a little bit high in this week. And again, it's because as the season changed in Serbia and the area that is close to Serbia, there is a lot of wood burning and other sources of BB, for example, dirty technologies that come from industries, and they contribute to the rise of the ratio of BB in the total of BC concentration. That is it.
Very much for your presentation. Any questions? Let's check online. Any questions online?
I have to click on that talking. I was so lost. See how difficult is it?
It's confusing, yeah.
So you probably just stop share and that must be no, here we are. I don't see any question online, is there it? Probably not. Okay, thank you.
Thank you very much.
And so looking at the schedule and
Yep.
do we have a camera on? Yeah.
It's on.
Yeah, now I see, yes. So I would like to thank everybody in the room and also online, and probably already head towards closing the workshop. So it has been really nice time. I believe we have learned a lot, and thank you, especially those who came here in person. And the last words would be just that let's hope to continue in the current work, and let's hope we will meet again next year, all healthy and alive, and place the basically dust research into proper aerosol kind of wide topic conference. Okay, so thank you very much, and thank you also those online, and have a great
Thanks to you
afternoon.
to get us together every year.
You'll still take